Okay, so the key thing is we have preclinical studies, which are the lowest level of the evidence pyramid, and then we're going up to increase the validity of the studies. So case reports, case series usually are they're very low level of evidence because it's based upon one person's experience, it's one case, it's a number of patients, it doesn't take into account a lot of stuff, and usually it's retrospective. Case control studies are always retrospective by and large. So you have one group with the intervention that you want to investigate, and your case control is the control group of healthy patients or the gold standard of care. Again, case control is retrospective. Cohort studies, you're following the same group of patients prospectively. And that is why a cohort study is above a case control study. Randomized control trial sits at the top of the pyramid, second only to a high quality meta-analysis or systematic review, which pools very high level quality of studies together to achieve an outcome. So the reason why a randomized control trial is at the top is because it is prospective, it is usually blinded, it's the least amount of bias compared to the others in the pyramid. When we look at data, one of the first questions you should ask yourselves, if you're given a data set of 100 by 100, 1,000 by 1,000, you should always ask yourself, is the data normally distributed? That's the first question you should always ask yourself. So if the data is normally distributed, it means that it's probably correct, because healthcare data, age, patient-reported outcome measures, pain scores are usually normally distributed. You have patients who are right on the spectrum of pain threshold, lots of pain, no pain, but most patients fit around the middle of this bell-shaped curve. Classic FRCS question, what is dispersion? It is basically extent to which the data is spread. You only need to know this for the FRCS. No real researcher uses these words. Central tendency mean is basically the single value that attempts to describe a set of data by identifying the central position within that set of data. So that's the key. Central tendency mean in a normally distributed data is basically the mean. Okay. So when we look at these two, for example, so you have here on the left, you've got normally distributed data. On the right, you can see how it's skewed to one side. It is skewed, which means that it is not normally distributed. And the reason why this is important is after plotting these data points, you need to decide if you are going to apply a parametric or a non-parametric test. Okay. A parametric test is for normally distributed data. So that's a bell-shaped curve. You are going to be using a parametric test. Okay. You are looking at the mean. Okay. Remember what we said? The mean. Okay. This is normally distributed. So you're looking at the mean. Okay. So you're using a parametric data. You would have seen, if from papers that you've read, you would have seen references to two sample t-test or a paired t-test or a Pearson coefficient of correlation. You can only do these tests if the data is normally distributed, okay? Because these tests work with the mean, okay? A two sample t-test and a paired t-test are important for you to know, because those are, again, quite common questions that people may ask you. Essentially, a t-test, you are comparing the mean between two independent groups. So as an example, do managers who are men have higher average salaries than managers that are female? So your first group is men's salaries, your second group is female salaries. You're going to compare the mean of both of those. If you plotted those two data, it will be a normally distributed data. Okay. A paired t-test is looking at the same individual, but before and after an event. Okay. So for example, you're looking at a student's diagnostic test results before and after a unit of study. So say you've got a intervention, you want to look at the preoperative and the postoperative patient reported outcome measure for that one patient. You're going to look at the mean before the intervention and after the intervention and see what the difference is. So paired t-test, it's the same individual, but it's a before and after test. Okay. No one's going to start questioning you about what is a Wilcoxon rank sum test or a Kruskal-Wallis and how does that work and what's the theory behind a Kruskal-Wallis. But you have to understand the difference between a parametric and a non-parametric test. But more than that, you also have to understand the difference between a two-sample t-test and a paired t-test, because these are often the most common tests that you'll come across. The non-parametric version of these two-sample t-test and paired t-test is called a Wilcoxon test. Okay, so if we look at this data set, so we want to compare load times of a video game. Okay, now we've got the load times, we've got an Excel file, we've got one column that has all of the load times. So some load times it can take up 2.5 hours. Can somebody please mute whoever that is? Yeah. Okay. So so we want to look at the load times. And so we'll have we'll have people who are video games which load at 17.5 hours, some that load at it takes very quickly and doesn't load at all. And we plot all of this in a histogram. Okay. We want to look at the distribution. And you can see here, it's not really distributed around the mean. The mean, I would say, is probably about 7.5, and it doesn't look like a bell-shaped curve. It's skewed to one side. This is a negatively skewed data. Now, we have two options here. We can use a non-parametric test, okay, to analyze the difference between the load times, or we can manipulate this data to change it to normally distributed. So we have two options when analyzing this data set. Does everyone understand that? Does everyone make sense? Just because it is not normally distributed does not mean that it is bad data. It just means that you have to use a different test or you have to do something to that data. So just again, very classic FRCS questions that come up time and time again. When do you use a parametric test and when do you use a non-parametric test? So hopefully everyone should be able to answer that question. If somebody has any clarifications or wants to ask further questions about parametric and non-parametric, speak up now. Okay, sounds
Just put your hand up and
yeah,
and I'll verify it for you.
Yeah. Okay, sounds like everyone's kind of understood that, which is good. Okay, no one's got any questions. Good, because it's a super question. Yep.
Omar, so I'm asking about the variance. What's the variance in relation to these things?
Yeah, so good question. Okay, so variance is related to your standard deviation. Okay, so variance is basically how the data fits around the mean. Okay, so you can have data that is very, very, so a good example, say you have data points between 1 and 2, and most of the data is around 1.5, but you have a couple of points that are extreme end. The variance for that is very different to data points where it is dispersed evenly between 1 and 2. So the variance talks about the dispersion and the weighting that you have on that dispersion. Does that make sense? So it's almost like another surrogate marker for standard deviation, how far it is away from the mean, but it applies a weighting to that. Yeah. Does that make sense? Does anyone else have any?
Thank you.
No? Okay. So when we, again, so classic example, the classic question is, how do you know if the sample comes from a Gaussian distribution? Gaussian distribution is a normally distributed data. So don't get caught out. Gaussian is just a normal bell-shaped curved data. So the answer to this question, if this comes up in the exams, is I'm going to plot the data on a histogram. That's the first thing. I can also do various tests to see if the sample comes from a Gaussian distribution. And that's all. There are very fancy tests such as a Shapiro-Wilk test and a Kolgarov-Smirnov test. However, the key thing to note is I will plot the data on a histogram to see if it is normally distributed. You could ask is, what happens if you use the wrong test? Let's assume that you have normally distributed data, but it doesn't report. Oh, okay. If you have normally distributed data, but you're reporting, but somebody's reported and used a Wilcoxon rank sum test. It is not ideal. The answer is it's not ideal, but it really depends on the sample size and what test they've applied to that sample size. That's all you need to know. It doesn't mean that it is 100% wrong. It just means that you have to investigate why the wrong test was used. Cool. Now, this is a very, very important topic, sensitivity and specificity. So sensitivity refers to a test's ability to diagnose an individual with a disease as positive. Okay. The specificity is its ability to designate an individual who does not have the disease as negative. You have to know the difference between sensitivity and specificity. But more importantly, and this is where everyone makes loads of mistakes in the FRCS on this section, is what is the difference between sensitivity and positive predictive value? Okay, so it's positive predictive value is probability that a patient with a positive test or an abnormal test actually has the disease. This is different to sensitivity. Okay, they almost sound the same, but they're not. With a positive predictive value, it is all about the test. With a sensitivity, it is all about the individual. So a positive predictive value, you're talking about the test first, okay? Because a predictive value is always, you're using predictive value mostly to assess how good a disease is, okay? Negative predictive value is probability that a patient with a negative disease actually, with a negative test result, actually does not have the disease. Okay. Does that make sense? Because this is really, really important. Like everyone gets caught out in this. Okay. So if I said a test has a positive predictive value of 0.6, what does that mean? Anyone know? Positive predictive value of 0.6.
It means that they just a second, I'm sorry. A positive predictive value, it means that the probability that it's 60% that if the test is positive, this patient will have the disease.
Yes, yeah, exactly. Yeah. So you are looking at the test, then the individual. Good. Okay. What if I told you that test had a positive predictive value of 0.9, but the sensitivity, but the negative predictive value was 0.3.
So it means that if the test is positive, it's 90% a chance that this person is positive for the disease. And if it's negative, it's 30% a chance that they don't have the disease.
Yeah, but hang on, but negative predictive value, it's somebody who has a negative test result.
Yeah.
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 Yeah. Good. Good. Just always make sure that that bit is very, very clear. Would you use that test?
It depends on what I'm using it for. If I'm using it for screening, so yes, it's a good test. If I'm using it, yes, I'd use it if I'm using it for screening, basically, because it's sensitivity or what I care about.
But we haven't talked about sensitivity. We've only talked about positive predictive value and negative predictive value.
But still tells you it's about the same concept, what you need to know. If it's a test is sensitive or a test has a high positive predictive value, they both will give you the same kind of information. It means that if the test is positive, it's highly likely that the patient will have a disease. If you look from the sensitivity point of view, you're looking from it's basically the egg or the chicken, which came first, but both will give you the same information.
See, what you're doing is you're conflating sensitivity and positive predictive value.
Yeah.
Probably, yes.
You can have tests that have a very good or a moderately good positive predictive value of say 0.8 and a sensitivity of 0.4.
Okay.
So again, if you have a test that has a positive predictive value of 0.9 and a negative predictive value of 0.4, and your examiner's asking you, is that a good test? Your answer is correct, I agree, which is it depends on what you're testing. Okay. And that's always, you should never confidently just say yes. Okay. But also be aware that a positive predictive value of 0.9 or 90% is very good. That's a very good test. Whatever the metric is, whatever you're testing, 90% is a very, very good test. But you answered that very well in terms of, yeah, it depends on what the test is, what is it measuring, all of that. So when we're looking at, so this table is called a confusion matrix or a 2x2 contingency table. Make sure you know these calculations very, very well, because you will get asked about that. You could very well get asked about this. Okay. There was one guy I know who had to draw it out, and they, and I'm sure Hashim, you've probably done lots of mocks where people draw it out and they get confused about what's A, what's B, what's C, what's positive, what's negative. Okay. Now, here's a question. If you had an AI model that was able to diagnose a fracture and it had a sensitivity of 0.8, but a specificity of 0.3, would you use that AI model in the hospital? Okay, why? Explain the sensitivity of 0.8 and the specificity of 0.3.
So sensitivity is how sensitive the disease to pick up positive cases, but not to confirm it. This is my understanding about it. So if the sensitivity is 80%, that means I have 80% chance.
Let's just stop there. Say your answer again, because I think you said it wrong. So I just want to make sure before we just talk about that point.
I said the sensitivity is, I understand that it is how sensitive the test to detect positive cases. Is wrong?
So what's the difference?
Not to confirm it.
Okay.
But because the specificity is the ability of the test to exclude negative cases and be specific to the disease. So the sensitivity, you can use it as a screening test. So if I have an 80% sensitivity, I can use it as a screening test, but I will need another test with a higher specificity to confirm it, like ELISA and Western blot for the HIV. So ELISA is a sensitive test, has a high sensitivity, but it's not a confirmatory test. I need a test like the Western blot with a high specificity that can exclude negative cases.
Okay, so would you use that AI software?
I will use it initially to screen if it is a software and it has a low cost, not time consuming and appealing by the patients and convenient to us and rapid. That I will use it as a screening test, not as a confirmatory test.
Okay. What is, out of all of these metrics that you have in front of you, from sensitivity, specificity, positive predictive value, negative predictive value, which one is the most important?
Again, it depends what purpose are you using the test for. If you are searching for a screening test, I would say the sensitivity and the positive predictive value.
Okay, interesting. Okay, I tried to push you there to give an answer. So there is a correct answer, which is actually a positive predictive value is universally considered the best single metric in any 2x2 contingency table. But no one really looks at the negative predictive value, and the sensitivity is great as a screening test, as you said, to capture your overall thing. But ultimately, if you're testing a diagnostic test or a software or anything like that, you want to be able to tell and determine what the actual reality of that individual case is, and the positive predictive value is usually the best metric. Even positive predictive value is probably actually more important than accuracy. But yeah, your answer again, good. That is a very FRCS question. They don't want you to commit. You gave a very coherent answer, which is it depends on what the question is. Sensitivity is great for screening. Like, that's very good. Okay, good. Does everyone understand that? Does anyone have any questions? Good. Okay. So the next thing that we're going to talk about is data analysis. So does anyone know what this is?
Box plot.
Box plot. Good. Okay. So I'm going to point. Can you see my mouse? Can everyone see my mouse?
Yeah.
Okay. I'm going to point to something and I want you to tell me what it represents. Okay. What's this?
I think the upper quartile.
Okay. It's not, but okay. So what's this?
This will be.
Oh, hang on, my mouse is on.
This is the median.
Okay.
Median, yeah.
Okay. And what's this?
This is the quartile.
The lower. Yeah.
Yeah. Good. Okay. So this is interesting. Okay. So if you have a point here, what's the point here? If there was a point here.
It will be an
Outside.
outlier.
Yeah, good. So when we look at a box plot, okay, what we're looking at is basically, so this is the upper quartile. Okay. So what we're looking at, sorry, this is the max value. So you said this was the upper quartile. You said this was the upper quartile. This is usually the max value outside of the outliers. The outliers sit completely outside the box and whisker plot. Okay. It's usually the maximum and the minimum. And then you have your upper quartile, lower quartile, and then you have your median. Okay. And this region here is your interquartile range. Okay. Does that make sense? Does everyone understand that? Because I can't go on to the next bit, which is really important because this is often asked. Okay. Yeah. Does everyone understand that? So here's a question. Can you tell? So say these are four results. Okay. And you're looking at 4 groups of patients. Okay. Can you tell from looking at just this box and whisker plot if there is a statistically significant difference between them, between these 4 groups?
as long as there is overlap between the boxes, I think there is no significant difference.
Interesting. So you said the boxes, there's no overlap.
Yeah.
I think
Okay.
the whole
The
thing.
interquartile bit of the graph.
Okay. Interesting. So if you see here, it's all about the median, right? Remember what we said earlier when we talked about parametric and non-parametric tests, right? So what you're doing in a non-parametric test is you are comparing the two medians, right? In a parametric test, such as a t-test or a paired t-test, you are comparing the means, okay? If you are looking at a box and whisker plot and you have the median, okay, and you see what you're really doing is you are comparing the two medians and their relation to each other, okay? And so it's the median. If the median of one group lies higher, lower, whatever, different or outside the upper quartile or the lower quartile range, then you can probably make an inference that there is a statistically significant difference. Okay? Does that make sense?
Sorry, even if it is
Even
away
if,
from the box, you say?
Yeah, even if the boxes, there is a slight overlap in the boxes, if the median in those box and whisker plots is above the quartile range, then you can make an inference that there's probably a statistically significant difference.
Yeah.
When you have your interquartile range, so another useful thing about box and whisker plots, and I'm a big fan of box and whisker plots, is the other thing that you can tell when you're looking at this is, number one, not just if there may be statistically significant difference. So here, the blue and the green, there probably is a difference between the blue and the green groups. Like it's because this median sits below the lower quartile of the green box. Okay. The other interesting thing that you can tell is how we talked about variance earlier and a standard deviation, but interquartile range is such a good metric it's such a good metric to interpret data. What I mean by that is, can you see the width of the boxes? Okay, the width of the box here, so 75th percentile minus the 25th percentile, so the upper quartile and the lower quartile. If you have a very narrow box, that data, most of your patients or your group seem to fit around a very small narrow margin. So what that tells you is it probably tells you that the confidence interval is probably very narrow. Okay. So it tells you that the groups all fit around the same kind of point. Okay. Whereas if you have a box plot where the interquartile range is really high, it tells you that there's such a wide distribution, a wide variation in that data, in that group, that it's very hard to interpret. So a box and whisker plot gives you a really good snapshot of the data, right? A very good snapshot of the data. It's the same as your max value and your minimum value. If the whiskers, so your max value and your minimum value, are really long, are very long, it means again that the data is really quite wide. Okay, that you've got two huge, you've got 2 points of data either side that's telling you that's not conforming to the rest of the data. Does that make sense? Does anyone have any questions about this? Because this is something that you can tell a lot. So you could be given a box and whisker plot of 2 different groups and without very little information, and they'll ask you, can you tell us a bit about what you're seeing? Okay, so you comment and you say there is a range, a wide range because of the maximum and the minimum here. You've got your interquartile range, tells you that the group is probably, most of the patients or it's usually patients, will fit into a very narrow distribution. Okay, so you've got a narrow bell-shaped curve, very narrow. They mostly fit around that middle. Okay, and if you've got two groups, you can compare the median relative to the other one. Okay, does that all make sense, guys?
So the only confusion here is when we read about the forest plot, they say the
This is
maximum.
not a forest plot. This is not a
Yeah,
forest plot.
but
Yeah.
I
We'll go
mean,
onto a forest plot. We'll go onto a forest plot. Yeah.
but so the median here is the thing which is causing the significant or the statistical significance, not about the range.
No, what you're inferring here is the median of one group relative to the interquartile rate, relative to the to the box of the other group. That's it. So you're not saying that there is statistical significance. You're saying that based upon this box and whisker plot, I suspect there probably is a significance difference between the two groups. Does that make sense? Because the median lies, the median line lies outside of the other box.
Yeah.
We'll talk about forest plots, so don't get too confused. This is just a box and whisker plot. If you're given this box and whisker plot and you're expected to interpret it with very little information, this is true data analysis. Okay? You're making inferences. You're not saying that this is definite. You're saying that based upon this graph with limited information, this is what I can tell. Does that make sense?
Yeah, thank you.
Okay. So we can talk about Kaplan-Meier or we can talk about forest plots. Should we go to talk about forest plots first then, and then talk about Kaplan-Meier, Ahmed? Would that be easier for you?
Yeah, it will be very good comparison, please. It will be good.
Okay, good. Okay,
Thanks.
so let's talk about forest plots. So forest plots, Ahmed, since you're there, what is a forest plot?
So forest plot is the
This is very blurry.
multi-analysis.
Yeah, what is a forest plot? Yeah.
Yeah, so forest plot is multi-analysis study, and on the left side, this is the studies on the all of it having a confidence interval of 95%, and then the vertical line in the middle, which is the zero, showing that the sum of the both it means that that some of the groups is like insignificant, and the power of the study, the bigger the books, the more power it has, and the rhomboid shape in the end is the sum of all these studies.
Okay, good. So interpret this for me. Sorry, I know it's very blurry. So what is, yeah, tell me from this data. Sorry, I know it's yeah, it is very blurry. I'm just trying to figure out. Yeah. Can you tell me what can you infer from this data? Interpret this forest plot.
The thing, I cannot read the words. It is very blurry here.
Okay, so if I told you, so here it's study your group on the left side, you've got the number of events / total, experimental and control, and then you've got your risk difference. Okay, you've got your weight, and then you've got your risk difference here as well. Okay, so the numbers.
Yep. Yeah.
This favors experimental, this favors control, and then I can read out any of this stuff, so if you need to. So test of overall effect and whatever. So yeah, tell me what if I said to you that this is looking at a type of steroid injection in Neo-A patients compared to the control group, which is a placebo for pain relief improvement, what do you think? Can you interpret the result for me?
So what I can see is that like the first study had a wide range, which is a low power study, and it is crossing the vertical line.
Yep.
But most of the studies have a very good power, and the total of it is in favor of the fever experiment or the experimental. I don't know what's written down, but it is on the like side of the experimental study mentioned. So the sum of these studies showing that this test is a good test to or like a good experimental study, if it is clear.
Okay, fine. So would you use this?
Yeah, I would.
Okay.
Because the rhomboid sum of it is on the like we can say on 0.3 or something, and so that means that this is that it is, the risk difference is on the positive side, not
Okay.
zero.
Yep. Yep. Good. Okay, fine. Yeah, sorry, I know it's very blurry, so you can't tell, but that's fine. So one thing that you didn't mention, by the way, you answered that very well, very impressed. One thing you didn't mention is, and this is an absolute must when you're talking about when you're interpreting forest plots in your FRCS, or generally, you need to look at the heterogeneity. You absolutely have to look at the heterogeneity. It will be a number on the bottom right, so the test for heterogeneity, and it will look like a chi squared. Okay, heterogeneity. So you'll see a lot of badly written papers where people have pulled lots of data together, but because all of the studies are completely different. So one study is looking at steroid injections in patients who are under the age of 20. And another study is looking at patients who are over the age of 60. And the patients who are over the study with the patients over the age of 60 have way more patients and it's weighted way more towards them rather than the other study. You can't pull those two studies together, right? Because it's very heterogeneous. They're looking at completely different samples. So your heterogeneity is really high. It will be above 50%. If heterogeneity is above 50%, it's usually quite high. Okay? Does that make sense? So heterogeneity is really important. Anything above 50% heterogeneity in a forest plot, it's very hard to interpret. Like you should probably not interpret it. So that's really important. The other thing to look at whenever you're interpreting, and you've said this very well, but you forgot one other thing, which is to look at the weighting. Okay. Now, there is no study here that looks like it's really, really heavily weighted. But if there's sometimes you see lots of forest plots where you'll have two studies that make up the majority of the forest plot, and it's very heavily weighted towards those two studies, which means that you probably have a high heterogeneity despite any kind of output or result. Even if it's statistically significant, then you still have to be wary. You still have to comment. You should say all the studies appear to be reasonably weighted equally. Okay, so that's the second point that I think you missed out. And the third point to note, okay, and you said it really well, is you see this line here of 0 in the middle. And actually, it's probably this is a good time to kind of go through this. You see here this line of 0 in the middle. Okay, this is the line that signifies no difference. That if your rhomboid, your overall effect estimate, touches this line, okay, it means that it is not statistically significant. And what's even more so is if any line crosses this 0 line, okay, then it is not statistically significant. And you can tell, right? So the risk ratio here for this study was 0.6. It was not statistically significant because the confidence interval, okay, the confidence interval crossed 1. Okay, so this line tells you where the effect estimate is. Okay, so I'm going to repeat that again because this is really important. If your confidence interval crosses 1, you can immediately say that it is not statistically significant. So you see here, 0.06 to 5.99 definitely crosses 1, right? 0.06 to 5.99, that crosses the line of no difference. Okay, so without even drawing this out, just by looking at the numbers, you can tell that it is not statistically significant because it crosses that line of 1. Okay. Now, what's really interesting about forest plots, and if you guys ever read a very landmark paper called the Crash, very famous meta-analysis that basically looked at the benefits of corticosteroids in acute trauma, head trauma. So in the past, people used to give corticosteroids whenever a patient came in with a traumatic brain injury or anything like that, and everyone assumed that this was good for the patient because steroids reduce inflammation, blah blah blah. A meta-analysis pooled all of the studies and found, and all of those studies that showed there was efficacy, but pooled all of the studies, and it turned out that it was not efficacious. And then randomized control trials spun off from that, which were very well conducted, which showed actually it increased mortality, which is what the meta-analysis showed. The reason why I'm telling you this story is you can still have 5 or 6 studies that have no statistically significant, but when they're pooled together, you can have statistical significance. Okay. Does that make sense, guys? Okay. And when I was talking about heterogeneity earlier and the chi-squared test, this is what I was referring to, not this. This is called chi, but this is the chi-squared. Okay. Can everyone see my mouse? Yeah. This is the chi-squared. This is your test of heterogeneity, not this. This is a very common misunderstanding for FRCS in the FRCS candidates. Chi-squared is this. It's the I. Okay. And if it is 0%, it's a very good test. It means that the tests are homogeneous. They are very similar. They are not heterogeneous. If it is above 50%, then they are very heterogeneous. Okay. Does that make sense, guys?
It does. Sorry, Omar, just a question.
Yeah, go ahead.
So the heterogeneity, if you don't have this I to the power 2, can you check the p-value for, I think it's different from the normal
Yeah.
p-value that we use, right?
Yeah, so the test of overall effect p-value is here. And the test for the heterogeneity, you can look at the p-value if you want, but it's not the test of heterogeneity. Your test of heterogeneity when you're commenting on a forest plot to your examiner will always be the chi-squared. Like, this is how you get those easy marks. This is how you get the 8 and 9, like this is the test that you measure, that you comment on. It's the chi-squared. And typically anything less than 40, 50% is okay. Anything above 50%, it's very heterogeneous. Okay. The p-value that you're referring to is the test of overall effect, and this reflects the position of this rhomboid here. Does that make sense? You can say
Yeah,
no.
it does. No, it does. It does. It perfectly does. So the p-value for the overall effect, it has the same rule as the p-value that we normally use, the 5%.
Yes, 0.05. Yes.
Okay, thank you.
What you can also tell, okay, without even looking at the p-value, you can tell that it is not statistically significant, right? Because the rhomboid is touching the 1, okay, here, but it's nearly statistically significant because the rhomboid is just about touching. Even more so is, you see here, this is the confidence interval for the total effect, okay? The confidence interval goes from 0.36 to 1.15. It crosses 1, but only just. which is why your p-value is nearly 0.05, but not quite. Does that make sense?
Yeah, it does.
So you can check your answer. You're like, well, this is not statistically significant. I'm just going to make sure this is not statistically significant. Yep, the confidence interval crosses 1. Yep, the p-value is higher than 0.05. So yeah, this is not statistically significant, but you want to get the high marks, and you could say it's very close. It's very close. And the reason why it's close is you can see here in the overall effect estimate is just about touching the 1. You have a very narrow confidence interval that just about crosses the 1, and your p-value is nearly 0.05. So that's how you get the high marks, because not only do you know how to interpret your forest plot, but you understand what's actually the components of the forest plot to basic medical statistics. Does that all make sense, guys? Yeah? So it sounds like everyone's pretty happy with the forest plots. So now we're going to talk about survival curves. Okay, so let's go, and I want you guys, anyone who knows. Okay, so you have 2 survival curves. You have your first group, which could be your intervention group, or it could be your control group. So for the sake of this, let's say that the red line is your intervention group and your green line is your control group. Okay, can somebody tell me which group is the better group?
The green one?
The green one.
Okay, good, good. Why?
Because
Because
at any point of time, you have more survival probability compared to the red group. And at the end, which is at 1200, I'm not sure about the unit,
Yeah.
but you have more than 50% survival probability in the green group and less than 50% of survival probability in the red group.
Okay, good. Now, somebody else, tell me, what is this drop? What is this drop? What does this mean?
It means that some patient has been lost or died or didn't complete the.
No. So be very careful. Again, this is FRCS. You have to be exact. What is the drop?
So
you
the drop, I think it's that patient is not lost. I mean, failure,
Good.
simply.
Event. It's the event. Whatever it is.
The event has happened, has occurred. The one with the patient is lost.
So just to interrupt, again, we want to be precise in this exam because I want you guys to do well and get the high marks, not just scrape the pass. So it's the event of interest. Okay, the outcome or event of interest. Okay, the reason why I picked you because you said lost to follow up and you said they died. So let me give you a good example, right? So let's say that here, my event of interest is my event of interest is my event of interest is revision. Okay, just revision. That's it. Revision knee. Revision of a knee replacement, knee arthroplasty. Okay. Every time this is dropped, a revision has happened. Okay. However, what if a patient dies because they've been hit by a car accident before they've had their revision knee or during the study? How do we capture that patient who died?
These are the
censoring.
Censoring.
Good. And so what happens if a patient, I've tried to contact a patient, okay, and I can't get through to them?
This is censoring as well. That's why we bought this censoring on the these dashes.
Good. And that's your loss to follow-up, right? So your loss to follow-up is not captured in this drop. Your loss to follow-up and any event or outcome of interest, any event or outcome that is not of interest, but relevant to your study population is captured by this dashed line. Okay? That's your censoring. This patient, another patient. one patient here, 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 one patient here. This is really important because you can often find in some survival curves, you have a look and you see, wow, this intervention is so much better than another intervention, but you have such a huge loss to follow up, or you have patients who have received a different outcome. That means that they are censored. Okay.
Yeah.
Does that make sense, guys?
Yeah.
Okay. Now, when we look at your Kaplan-Meier estimate, what metric is the most useful metric? What's your most useful metric? Because you all said that the blue line is better than the red line. Green line is better than the red line. Okay, because
You have to look into the confidence interval as well.
Oh, good. But more importantly, what is it? Is it the 50% median survival? Is it the what is it that you're looking at this here? So if you're looking at survival probability, your Kaplan-Meier, so it's 50%. Okay, so your 50% is your biggest metric for determining the outcome in treatment effect between two groups. Okay, that is your absolutely ideal metric. It's your survival probability at the 50% mark. Okay, now you've mentioned the confidence interval. So this is what this blue shading is around your Kaplan-Meier survival curve. Okay, so why this is important is if you look here, both of these, so you can kind of say, actually, do you know what? The green line looks really good. This is a pretty good treatment. It's better than the red one. More patients survived. The censoring is roughly the same. There's not a huge difference. But look at how wide that confidence interval is. That's a very wide confidence interval. That tells me, in the same way as the red treatment group, that tells me that there is something I need to investigate more about why there is such a big, wide confidence interval. Remember, your ideal treatment is a treatment that has a very narrow confidence interval because it means that you can predict with certainty that if you gave this treatment to somebody, the effect size will be as low as this and as high as this. It is a narrow confidence interval. Okay, so here you've got much narrower confidence intervals between the two different treatments. This is a better survival curve. This is not a very good survival curve because the treatment effect was so wide. Okay, does that make sense, guys?
Yeah.
Cool. So that's the key things. Now, the last thing that I'm going to talk about is, does anyone know what this is?
Can I just ask a question about the Kaplan-Meier before we move on? Actually,
Absolutely.
two questions. I'm sorry for that.
Yeah.
First one, censoring. They are not failures because they didn't fail, but how do we deal with them? Is it just like intention to treat or per protocol, or so what is the point of keeping the number and what do we do with them? How do we analyze them?
Yeah. So number one, so how you analyze a Kaplan-Meier, you're analyzing, there's a number of metrics. So the first one is you're looking at the survival probability, usually at the 50% mark, right? So that's kind of the key metric. Okay. So that's what you're comparing and you're doing your p-value at the 50% mark. Okay. Your median survival time. The median survival time is number one. Okay. Number two, the number of patients who have been censored should be equivalent in both groups. If they're not, it means that it's another data point that you need to comment on. And the reason I mention this is, imagine if this was two physiotherapy protocols, okay? So two physiotherapy protocols, and for sake of argument, we can look at the outcome measure as, actually, therapy protocol is probably a bad one. Let's say that you've got an implantable biologic. Okay, you've got an implantable biologic that is and your outcome measure is mortality. Okay, so you can see here that the green line is a better implantable biologic than the red line. But what happens on not implantable, a wearable biologic? Okay, but what happens if there is a higher number of censored patients in one group or the other? Okay, what that tells you is yes, that biologic was probably better, but the adherence was a lot worse because you had a lot more censored patients because a lot more refused to wear it. So a lot were lost to follow up. And that's why you need to see how many patients were censored. Okay, because if there is a big disparity in censoring between the two groups, there is something wrong in your study design. They should be equal. They should have an equal number of patients lost to follow up or who have had a different kind of outcome. Does that make sense? Does that
Yeah,
answer
it
your
does. Yeah, it does. Just one more question. Can you go to the other Kaplan-Meier curve, the one you started on?
Yeah,
So on the y-axis, that's the survival probability.
yeah,
My question is, when you started the study, say you started with 100 patients on each arm, okay?
yeah,
And then every time you have a dip, the patient, some failed and some censored. So theoretically, you have less numbers. So you say started the line with the 100. After the first dip, you have 90 patients, okay? But
yeah.
what if that's an ongoing study, like for example, the NJR? Is it possible that you started with 100, but after a dip, because you recruited some more new patients, you have now 300, for example, but it's not represented on the curve because on the y-axis, you're measuring survival probability. It's not the number of the patients. Does it make sense? Is that correct? Am I understanding right?
Yeah. So interesting. So the so what you're describing there, so your main question is, to answer your question, the NJR does not use a survival curve as a graph to show. If you look at the NJR, they look at outliers around a standardized mean for each surgeon. Does that make sense? A survival curve is a time to event. It is a time-based analysis, not a odds ratio or a cross-sectional based analysis. It is a time to event analysis.
Oh, I mean, forget about the NGR. Imagine this is an oncological study for like survival of patients, okay?
Yeah,
And you started at the very left of the curve with 100 patients, but as
yeah,
you go through time, you are recruiting more patients. So
yeah.
some of them will die. So that the 100 at 1 year, they are probably
Yeah,
90, but you
yeah,
recruited 100 more during the
yeah,
year.
yeah. Good question. Very good question. So the answer to that is very easy. So basically you will only do you'll only do a survival analysis over a period of time. If you're comparing two oncological diseases, so a lot of the randomized trials in oncology will do a 6-month 6-month safety and efficacy review. So they will look at all of the patients they've recruited in that 6 months, and they will then do a survival curve based upon that 6 months for those patients. And then they will do a year one, and then they will do their final 2-year one. The key thing is remember, you have an end point for those patients. So you're not just looking at mortality forever, right? You're looking at mortality at 1 month. You're looking at mortality at 3 months. The study will always quote mortality at a specific time point. Does that make sense? Like you'll
Yeah.
never analyze a patient if they have not reached the outcome point, end point. They have to have, so you can have 100 patients over a 6-month period, and then on the 5th month, you've recruited another patient, but your outcome is mortality at 6 months. That patient that you recruited at the 5-month point will not be included in your survival curve because it hasn't been 6 months.
Oh, yeah, it does make sense.
Does that
Yeah,
answer
yeah,
your question? Because you're
yeah,
never looking at mortality on its own. It's always be 30-day, 60-day, 90-day, 1 year, whatever.
yeah, yeah.
Okay, cool. Does anyone else have any questions on that? Okay, cool. The last one and the last thing we're going to talk about in terms of the data analysis is funnel plots. So funnel plots are rarely used, but they can come up in the exam. And to be honest, they're a bit silly because no one really reports on them anymore. They are basically tests of, they're more tests of the overall effect in the same way that a forest plot is. Okay. They're also, you can also infer bias from a funnel plot. Okay. And it tells you about the heterogeneity. It does a very similar thing to a forest plot. If all of the studies are in the blue line, it basically means that the test, your overall meta-analysis systematic test is not subject to a huge amount of bias. All of the effects are within what you would expect them to be. Okay. When you have each data point here represents each individual study. Okay. You have a line of effect in the same way that you have like a forest plot. Okay. And in those lines is where the studies are relative to that line of effect. It basically tells you what the effect of that study is. Okay. So as an example, so here you've got your overall effect is down the middle. Okay. And what it's done is you've pulled all of the studies, and that's where that overall effect is. And all of the studies that are within that fall within the 95% confidence interval. Okay. Does that make sense? It's very unlikely that you're going to get asked on funnel plots, but the only things that you're going to get asked, I suspect, and from reading past questions, is you're going to get asked, what is the blue line? What is this middle blue line? And what are these circle points? Those are pretty much most of the questions you'll get asked on a funnel plot. And this is for a meta-analysis. Remember, we're pooling all the results. Okay, cool. So if no one has any questions, does what we can do is I've got to go, but that is pretty much it for the data analysis side. And I'm happy to do another session. If you guys message Hashim, we can do another hour session.
So we need
on any other research-based topic. So if you guys message Hashim, and then we can do, we can do another topic based upon what you guys want. But I hope you guys found that useful.
Yeah, thank you very much.
Great, Omar. Thank you so much.
The funnel plot for the NGR data. Is there any possibility might be today or next time if we can just like go through it? What if it just came as a question in the exam?
Yeah,
how just like to nail it?
What? Yeah, definitely. We can definitely go through that. Why don't we, if you guys text or WhatsApp Hashim about any topics that you specifically want answering on, I will take a look. And if I think they're relevant to FRCS and they're likely to get asked, we can do the next session based on those. NJR funnel plots are definitely a good question.
Yeah, I think Omar, we need we can do the NGR one. And
Okay.
we can give him like a short brief how to appraise a paper.
Yeah, I've got a very good presentation on that. We can definitely do that. It's
okay.
Yeah, we can definitely do how to appraise a paper, and I can add on NJR. I'm happy to do that next week, Hashim. So why don't you guys, a similar time for me works really well. So Thursdays, between 6 and 7 start is really good. Doing more than 1 hour, I don't believe in doing more than 1 hour. So yeah, does that all make sense, guys?
Yeah. So and Thursday is almost free. So we can plan that. Don't worry.
Perfect. That works. That works very, very well. So perfect. That works very well. And Hashim, get all of the guys to add me on LinkedIn, and
Sure.
add me onto the WhatsApp group as well. And
Sure.
then on the WhatsApp group, you guys, yeah. So we'll do how to critique a paper, and we'll do
Yeah.
NJR funnel plots next week on
Yes.
Thursday. Hashim, if you guys please send me a link, because it becomes a nightmare if it's not on my calendar. I will 100% get very lost. So
No, don't worry, leave it with me.
please send me the Zoom invitation. Thanks, guys.
Thank you so much, Omar. Very good presentation, and I think we all need it. Thanks for your time, and I think
No
all of us appreciate it. So
No, guys. I'm happy to help out anytime. So
thanks so much.
next week, Thursday, happy to go through critiquing a paper. Very good, and we can go through funnel plots, NJR funnel plots.
I'll
Very
send you
good.
the invitation, and I'll send you a reminder before. Don't worry.
No worries, guys.
Perfect. Thanks,
Okay.
Omar. Have a good evening.
Thank you.
Guys.
Thanks, guys.
Thank you, Omar.
Thank you.